Hi, hello. This video is about superposition theorem. Okay, so what is superposition theorem? So in general, the theorem can be used to do the following. Okay, so we can analyze networks that have two or more sources that are not in series or in parallel. Okay, so this theorem is applicable if we have a circuit having two or more either voltage source or current sources. Okay, so this revealed the effect of each source on a particular quantity of interest. And for sources of different types, such as DC and AC, which affect the parameters of the network in a different manner, okay, and apply a separate analysis for each type, with the total result simply the algebraic sum of the results. Okay, so in this in superposition theorem, we are going to analyze each of the following sources individually, and then later on we're going to combine them together. Okay, so the superposition theorem states the following. So the current through or voltage across any element of a network is equal to the algebraic sum of the currents or voltages produced independently by each source. So we're going to analyze each of the different sources individually, and then later on we're going to combine them. Okay, so how are we going to do this? How are we going to just analyze one of the sources, and then how are we going to neglect the others while we are analyzing one specific source? Okay, so it says here that if we are to consider the effects of each source, the other sources obviously must be removed. Okay, so there are two types of sources that we're going to discuss. So we have a voltage source and a current source. So how are we going to remove them? So first, by setting a voltage source to 0 volts, is like placing a short circuit across its terminal. So definitely our question is, how are we going to kill a voltage source? Okay, so how are we going to eliminate the effect of a voltage source? So in this case, what we're going to do is we're going to place that voltage source by a short circuit. Okay, just like what we have here. Okay, so how are we for example, we wanted to remove this one. Okay, so we are analyzing using superposition theorem, and we wanted to remove this source here. How are we going to do that? We are going to replace that by using a short circuit. Okay, on the other hand, how about a current source? If we have a current source in the circuit, and then we have to remove it first because we're analyzing other parts of the other sources in the circuit, what are we going to do? So setting a current source to 0 amperes is like replacing it with an open circuit. So just like in this case. Okay, so for example, we have a current source here, and we have to remove it. We have to kill it for a while. So what are we going to do? We're just going to replace the current source with an open circuit. So as simple as that. Voltage sources are replaced by short circuits, while current sources are replaced by open circuits. Okay, so you have to remember those things. Okay, so if a particular current of a network is to be determined, the contribution to that current must be determined for each source. Okay, so if we have two sources, therefore there are two different currents that will be produced by each of these sources. So we have to analyze them separately. So when the effect of each source has been determined, those currents in the same direction are added. So we will be trying to see if if those two currents are in the same direction or in the opposite direction. So if they are in the same direction, what are we going to do? We're going to add those currents, okay, or voltages, and those having opposite directions are being subtracted. Okay, so the algebraic sum is being determined. So the total result is the direction of the larger sum and the magnitude of the of the difference. So whichever is higher between the two, or of the three, for example, so whichever is the highest value, we will be following the sign or the polarity for that specific magnitude. So similarly, if a particular voltage of a network is to be determined, the contribution to that voltage must be determined for each source. Okay, so if we wanted to solve for a voltage, for example, so the contribution to that voltage must be determined for each source. When the effect of a source has been determined, those voltages with same polarity, we're going to add them. Okay, so and those with opposite polarities, we're going to subtract them. So therefore, the algebraic sum is being determined. Okay, so which polarity are we going to follow? So the total result has the polarity of the larger sum and the magnitude of their differences. Okay, so if they have the same polarity, no problem, we simply add them. But if they have different polarities, we really have to subtract them. And then we follow the polarity of the one which has a larger value. Superposition cannot be applied to power effects, okay? Because the power is related to the square of the voltage across a resistor or the current through a resistor. Okay, so if we're going to get the power formula in the power dissipated in a certain resistance, if we're going to make use of voltage, it is equivalent to V squared all over R. Or if we're going to make use of current, it is I squared multiplied by R. Okay, so we cannot apply the superposition theorem to power effects. Okay, we are going to use only the superposition theorem if the relationship within the variables are linear. Okay, so what do we mean by linear? So just like current and voltage, so using Ohm's law, their relationship is linear. Okay, so the squared term results in a nonlinear. So when we say nonlinear, a curve and not a straight line. Okay, so a nonlinear relationship between the power and the determining current or voltage. Okay, so for example, when we are going to double the current through a resistor, it doesn't mean that you're also doubling the power to the resistor, okay, as defined by a linear relationship. But in fact, if we double the value of the current, we increases the power by a factor of 4. So why? Because of the squared in our formula, which is I squared multiplied by R. Okay? So tripling the current increases the power level by a factor of 9. And we do not just simply multiply it by 3. So therefore, superposition theorem are usually being implemented only when we are trying to solve for current and voltages because they have linear relationship. Okay, and we do not usually use this for power because they are considered non-linear. Okay, so how are we going to solve a problem or a circuit by superposition theorem? So let's start with our examples. Okay, example number 1. Okay, so using the superposition theorem, determine the current through resistor R2 for the network below. Okay, so we will be demonstrate that the superposition theorem is not applicable to power level. So we're going to prove that superposition theorem is only applicable for currents and voltages and not for power levels. Okay, so how are we going to do this? In this example, we have two sources. Okay, so we have a voltage source here. So we have a voltage source here and we have a current source here. So what are we going to do is we're going to solve this I2 here, okay, using the voltage source alone or the voltage source first and then followed by the current source alone. Okay, so we will do that individually. So we will be calling that I2 prime and then we're going to call the second solution as I2 prime. I2 double prime, and then we're going to combine those two. Okay, so how are we going to do that? So let us first solve this problem. Okay, when E acts alone. Okay, so when E acts alone, what are we going to do? We're going to treat this as an open circuit. So how do we turn off a current source? So we turn off a current source by replacing it with an open circuit. So our circuit now was simplified to this one. So this is just a series circuit, okay? Wherein your R1 is in series with your R2. So in this case, class, if we're going to follow the source here, wherein your current flows from negative to the positive of your supply, we can see that this will be the direction of your I2. Okay, so this will be the direction of our I2. And how do we solve for I2? Using this equation. Since this is just a simple series circuit, we know that our R total here, okay, our R total there is simply equal to 12 plus 6 ohms. So this will give us a total of 18 ohms. Okay, so knowing now your total current total resistance, we can solve for our total current. So the total current here is simply the total voltage, or our E, divided by the total resistance. So our E here is 36 volts divided by 18 ohms. So that will give us 2 amperes. Okay, but what we're concerned is this I2 here. So what is the current flowing across your 6 ohm resistance? And since this is a series circuit, okay, we can say that the current flowing across R1 is just equal to the current flowing across 6 ohms. So we can say that I2 prime here, let us call this I2 prime, not yet I2, because it is only the effect of E that we are dealing with. Okay, so I2 prime here is equivalent to 2 amperes. Okay, so that is the idea when your E is working alone or acting alone. Now, let's go to the second part. So for the second part, it is when your current source, okay, so when your current source acts alone. So what are we going to do so that your current source is the one which is acting on your circuit? So this is a voltage source. So therefore, if this is a voltage source, we are going to replace this by a short circuit. Okay, so we will bring back your current source here. Okay, so this is no longer open, but we are going to remove the voltage source by shorting this out. Okay, so what is the equivalent circuit for that? As you can see, we have here your R1. Your R1 is still there. Okay, this time this is your R2, and we have here your current source, which is equivalent to 9 amperes. Okay, so we can, since this is already a short circuit, we can just transfer your R1 here. Okay, so you can see we have two resistors in parallel and we have a current source. So what we're going to do here is just to make use of a current divider principle. Okay, by looking at the direction of your I here, it will flow in this manner. Okay, so technically this is our I2. We will be calling this as I2 prime, which is being which is the effect of our current source, and this is also your current here. So what is the current divider principle there? So let us call this I2 prime. So we are concerned with the current that will flow across our R2. Okay, so for current divider principle, we have here our total current, which is 9, multiplied by the opposite resistance. Okay, so since current is inversely proportional with the resistance, so therefore instead of writing 6 ohms in the numerator, we will be writing the 12 ohms in the numerator. So this is multiplied by 12 divided by the sum of these two resistors, which is equivalent to 18. Okay, so we have here this is 1, this is 2. Okay, so 12 divided by 2, so we have here 6 amperes. Okay, so for our for the effect of when I acts alone, our current I2 is equivalent to 6 amperes. Okay, so when your voltage source is acting alone, this is the direction of our current. Okay, when the current source is acting alone, this is the direction of your current. So as you can see, they have the same direction. So if they have the same direction, all we have to do is to add them. Okay, so therefore, if we wanted to solve for I2 here, I2 is simply I prime so I2 is simply I2 prime, which is the effect of your E, plus I2 double prime, which is the effect of your I. So why do we add them? Because they have the same direction. So this is equivalent to 2 amperes plus 6 amperes. So I2 now, by joining the two values, is equivalent to 8 amperes. So that is how you apply superposition theorem. So you just have to evaluate, or you have to analyze, or you have to solve the circuit one at a time. So if you remove one source, the other circuit will be a very, very simple type of circuit that can be solved using a simple series circuit like what we did, or simply a voltage or current divider circuit. Okay, so it also says here that we have to demonstrate the superposition theorem is not applicable to power levels. So how do we analyze that one? So for example, we are going to solve for power. Let us call this power prime. Okay, so that is the power which is being dissipated when we use the voltage source alone. So that is equivalent to 2 amperes. Okay, so that is 2 amperes squared multiplied by 6 ohms. So our power prime, okay, our power prime is equivalent to 2 squared times 6 ohms, and that is equivalent to 24 watts. Okay, so how about our power 2, power prime 2, okay? So this is the power being dissipated when your current I acts alone. So this is given by the formula 6 squared multiplied by 6 ohms. Okay, so that will give us 6 squared times 6. So that will give us 216 watts. Okay, now, how about the power being dissipated when the voltage source and the current source acts together? So that will give us power. Our power total now is equivalent to 8 squared multiplied by 6 ohms. So this will give us 384 watts. Okay, so how do we demonstrate that this is not applicable? Because if we add 24 and we add 216, that will not give us 384. So when we add 24 and 216, the result is only 240 watts, which is not equal to 284. Okay, so therefore, superposition only applies to current and voltages, but not to power levels. Okay, so it's as simple as that. Okay, let's go to another example. So we have here, using the superposition theorem, determine the current through the 12 ohm resistance in the figure below. So this is our 12 ohm resistance. So as you can see, we now have here two voltage sources. So for superposition theorem, what we're going to do is we're going to evaluate the value or the current I2 here using only one power source or voltage source at a time. So let us say we are now evaluating E1 only. Okay, so when E1 acts alone. So what happens when E1 acts alone? So what are we going to do with E2? We are going to make your E2 shorted. So we're going to kill E2. So this is already shorted. So if this is shorted, okay, we can redraw the circuit like this. Like this. We have already removed the effect of our E2. So this is now your 4. This is your 12. And this is our 24. Okay? So this is our 54 volts. Okay? So by looking at this 54 volts, and we're going to follow the polarity of this one, the current will flow from negative to positive. So therefore, the current will flow here, giving us this direction. Okay? So let us call that I2 prime. So let us call this I2 prime. This is the direction of your I2 prime. So how do we solve for I2 prime? This is a simple series parallel circuit. Okay? So the first thing we do is to get first the R equivalent for this circuit. So what is your R equivalent here? So the R equivalent is your 12, okay, parallel 4. And the 12 parallel 4 is in series with our 24 ohms resistor here. Okay? So making our R equivalent equal to 27 ohms. Okay. Now, what we're going to do is we need to get the value or the current flowing across this 12 ohm resistor. So we need to solve for the voltage across this one. So how do we solve the voltage across this one? We know that this 54 volts here will divide between 24 and 12 here. Okay, so 24 and 12 here. So whatever the voltage across this 12 volts here will be reflected to the 4 ohm resistor here. But that is not our concern anymore. All we need to know is to determine the voltage across this 12 ohms. Because once we know the voltage across this 12 ohms, we can determine the current flowing across that. Okay, so how are we going to determine that? We know that R equivalent is equal to 27. So we can solve for the total current. So what is the total current? The total current is 54 volts divided by 27 ohms. The total current is equivalent to 2 amperes. Okay. So the total current is the current which will flow across your R1. So therefore, we can solve for V1. Okay, so what is V1? V1 is 2 amperes times 24 ohms. So this is equivalent to 48 volts. Therefore, we can determine the voltage across R2. So let us call that V2. So what is V2? V2 is 54 minus 48 because this 54 will divide between 24 and 12. So if R1 has 48 volts, what will be the voltage across this 12 volts? So that is simply 54 minus 48. So therefore, V2 is equivalent to 6 volts. So knowing the voltage across this 12 ohms here, we can determine your I2 prime. So what is I2 prime? I2 prime is 6 volts divided by 12 ohms, giving us I2 prime equal to 0.5 amperes. Okay, so that is the current flowing across the 12 ohm resistor when the 54 volts source is acting alone. Okay, now we go to the next source. Okay, so what will happen when the 48 volts is the one which acts alone? So what are we going to do now is we're going to turn this on. Okay, and then we are going to short this. So we are going to make a short circuit out of this one. So if we're going to redraw, okay, so this time in this part, let us have here E2 acts alone. Okay, so when E2 acts alone, how does the circuit looks like? Just like earlier, okay? So we have here your 24, and then we have here your 12, we have here your 4, and then we have here your 48. Look at the polarity. Examine the polarity. Okay? So the current will flow from negative to the positive. So it will flow in this direction. Okay. Therefore, your I2 prime double prime is flowing in the opposite direction. Okay, so this again is like a simple series parallel circuit. So what are we going to do? We have to solve again for your R equivalent. So what is your R equivalent? So this is in parallel. Okay, so we have here 24, parallel 12, and the parallel combination is in series with 4 ohms. So we have here plus 4. Okay? So what is your R equivalent? So the R equivalent now is equal to 12 ohms. Then we solve for the total current. Okay? So what is the total current? The total current now is 48 divided by 12. 48 divided by 12, that will give us 4 amperes. Okay, so that is the current. Okay, so that is the current that will flow across the 4 ohm resistor. So what is the voltage across the 4 ohm resistor? So let us call that V3. So the voltage across V3 is 4 times 4, which is 16. Okay, so that is 16 volts. So that will give us the value of the voltage across your R2 when your 48 volts acts alone. So what is the voltage across R2? V2 is equal to 48 minus 16. Okay? So 48 minus 16, that will give us 32 volts. So we can solve for the value of I2 double prime. So I2 double prime is equivalent to 32 divided by 12. 32 divided by 12, that will give us 2.67 amperes. Okay, now, okay, look at the difference between example number 1 and example number 2. Due to 54 volts, the current is moving in this direction. Due to the negative 48 volts, the current is moving in this direction. So they are of the opposite direction. So I2 prime is 0.5 amperes while I2 double prime is equal to 2.67 amperes. So we're not going to add them. Okay, so we're not going to add them because they are of the opposite direction. What we're going to do is we're going to subtract them. And what sign are we going to follow? Okay, so is it in the downward direction like this one or in the upward direction like this one? So whichever is the higher value, we will be following that direction. So therefore here, your I2 now is equal to I2 double prime minus I2 prime. So this is equivalent to 2.67 minus 0.5. So therefore, I2 is equal to 2.17. 2.17 amperes. So this is our answer. Okay, so that is how you perform superposition theorem. Okay, so you solve first what will be the I value when E1 acts alone, and then you're going to solve what will be the value when E2 acts alone. So if you want, you can redraw the circuit, okay? Because the redrawn circuit will give you a very easy analysis, because like this one, it is the complicated circuit, or the when you're going to solve this with E1 and E2 together, you may use Kirchhoff's laws, you may use nodal analysis, you may use mesh analysis, or you can also make use of superposition theorem, wherein you're going to analyze them separately. So when you analyze them separately, your circuit is no longer a 2 voltage sources circuit, but rather it is already a 2 simple series parallel circuit, which is very easy to solve, and then you just combine them. Okay, so this is our second example. Let's go to our third example. Okay, so let us now go to example number 3. Okay, so using the superposition theorem, determine the current I1 for the given network. Okay, so again, we have two sources here. We have a voltage source and we have a current source. Okay, so let us determine the current I1 of the network. So this is the current I1. So let us first solve the circuit using the voltage source. So again, what will happen? So if we do that, this will serve as an open circuit. So if this is an open circuit, this is simply a series circuit. Okay, so since this is already open, so we can easily solve for I1. Let us call that I1 prime. Okay, so this is when E acts alone. So when E acts alone, what happens to your circuit is just a simple series circuit, wherein your I1 here, let us call that I1 prime, is simply equal to 30 volts divided by 6 ohms. So this is simply 5 amperes. Okay, so that happens when we remove the current source. So what will happen naman if we remove the voltage source? Okay, so if we remove the voltage source, look at what will happen. So this is no longer open. This is no longer open, but we have to kill your voltage source. So how are you going to do that? So we need to short this. Okay, so what do we have here, class? We have here, okay, a short circuit in parallel with a current source. Okay, so what do we have here? So if you are the current, okay, this current will separate. Okay, so they will split at this node. One will go here and the other one will go here. Imagine that you are the current. You have a resistance here which will oppose the flow of that current, and you have a short circuit here. Okay, so if you're the current, where will you flow? Are you going to flow here wherein you have a resistance that will oppose your flow, or are you going to go here at the short circuit path here? Okay, so in cases like this, always remember that the current always chooses the short circuit path because you have no resistance to oppose the flow of that specific current. Therefore, no current will flow across this 6 ohms. So when your current source is acting alone, our I1, let us call that I double prime, is equal to 0 amperes. Every time you see a current source in parallel with a short circuit, automatically a resistance in parallel with them will receive no current at all. Therefore, the current flowing across your 6 ohms here is equal to 0. So if we're now going to solve for I1, okay, combining the two different solutions, what do we have? So we have I1 prime plus I1 double prime. So I1 prime is 5 amperes plus 0. Therefore, we have I1 is equal to 5 amperes. So always remember that. Okay? So that is our example number 3. Okay, so let us now try to solve this example. Okay, so this is find the current through the 2 ohm resistor. So this is our 2 ohm resistor of the network below. Okay, so as you can see, we have 3 sources here. We have 2 voltage sources and we have 1 current source. So we have to treat them, or we have to solve them individually. Okay, so let us start first with E1. Okay, so what will happen when E1 when E1 acts alone? So when E1 acts alone, this becomes open. So this is open circuit and this is short circuit. Okay, so if we are going to redraw the circuit, it is like this. Just like a series circuit. Okay, so a simple series circuit. And the direction of your source, or the direction of your current, is this one. Negative to the positive. So let us call this I1 prime. Okay, so that is your I1 prime. This is 12. This is 2. And this is 4. Okay, so how are we going to solve for I here? I1 prime here is very simple. This is just a series circuit. So we have 12 volts divided by the total resistance of the circuit, which is 4 plus 2, which is equivalent to 6 ohms. So therefore, I1 prime here is equal to 2 amperes. Okay, so that is when your 12 volts acts alone. Okay, now how about when your E2 acts alone? Okay, so let's write it here. So what happens now is, this is no longer shorted. This is still open, okay, but we're going to make this shorted. Okay, so what happens? If we're going to redraw the circuit, it will look like this. So this is your 2. This is your 4. And this is your source. Okay, so again, a series circuit. Okay, so what is the direction? So this is 6 volts. So what will be the direction? Like this, negative to positive. So this is our I1 double prime. Look at their direction. They are opposite. Okay, and how are we going to solve for I2 double prime? Is simply 6 volts divided by the total resistance. What is the total resistance? 4 plus 2. So since this is just a series circuit, so this is 6 ohms. So I2 prime, double prime rather, is equal to 1 ampere. So we have 2 sources already. Okay, then we go to the third. Okay, so what happened to the third? So in the third set, this is no longer open. Okay, and this is still shorted. I'm sorry. So this is shorted, and this is also shorted. So what do we have is, okay, so when 3 amperes acts alone, it's like a current divider again. So this is your 2. This is your 3 amperes. And this is your 4. Okay, just like that. And if this is our source, okay, what will the current looks like? Okay, how will the current flow? So this is your currents. Okay, and we call this I triple prime. Okay, so in that direction. So what do we have here is current divider principle. And we wanted to solve for I triple prime. So we have here, since current is inversely proportional with the resistance, we have the total current, which is 3 amperes, multiplied by the opposite resistance, so we will have 4 in the numerator, plus the total resistance, which is 6. Okay, so cancel this out. I triple prime is equal to 2 amperes. Okay, now we have 3 currents and we have to combine them all. Okay, so by looking at the diagram, okay, by looking at the directions, we can say that this current here is the only one which opposes direction. Okay, so I2 prime here and I1 double prime and I1 triple prime shares the same direction. So how are we going to combine the 3 currents now? So if we wanted to solve for I1 now, we have I1 double prime plus we have I1 triple prime. So why do we add them? Because they share the same direction. And then we subtract I1 prime because it flows in the opposite direction. Okay, so we have 1 plus 2 minus 2 is equal to 1 ampere. Okay, so this is how we solve using superposition theorem. So when E1 acts alone, current I1 prime is 2 amperes. When E2 acts alone, current I double prime is 1 ampere. When I acts alone, current I triple prime is equivalent to 2 amperes. But when we combine them together, okay, so I1 double prime and I1 triple prime shares the same direction, so we add them. And then we subtract I1 prime because it flows in the opposite direction. Therefore, when the three of them is now acting together, the total current now is equal to 1 ampere. Okay? So this type of circuit can also be solved using Kirchhoff's laws. Okay? So this can also be solved using mesh analysis. This can also be solved using nodal analysis. And it can also be solved using superposition theorem. So in superposition theorem, it seems like the solution is longer because you have to compute for 3 different type of circuits like this one. But those 3 different types of circuits are already very, very simple circuit. Look, we only have here 2 series circuit and 1 current divider circuit. So therefore, although you have to solve for 3 different circuits, those 3 different circuits are already simplified. So therefore, although this has it takes you longer to solve, but the procedure or the process is just very, very simple. Okay, so that is how we solve a circuit using superposition theorem. Okay, so thank you very much and God bless.